Now we've got conductors in electrostatic equilibrium. And the word seems big, but let's just break it down and talk about what it actually says. So electro, meaning electricity, static, meaning not moving, equilibrium, meaning like the forces are balanced out on it. So electrostatic equilibrium is when charges are not moving on a, let me double check here. Oh, it's just when charges are not moving. Not even on something, just when charges are not flowing. So let's talk about the good properties. So these are the properties of a good conductor in electrostatic equilibrium. These charges are, these properties are first, that the electric field is zero inside the conductor. And that's good because if the electric field wasn't zero, there would be a force on all of the charges and they'd be moving around. So it wouldn't be in electrostatic equilibrium. Number two is that excess charge distributes itself on the outside surface. So that would be like if I have extra electrons on a ball, metal sphere, they're all going to sit just on that outside shell. Number three is that the electric field is pointing away from the conductor's surface. And perpendicular to the surface. Now it would be opposite if it was negative, then it'd be pointing towards and perpendicular, but you understand the sentiment. That it's pointing either directly away or directly towards, and that it's perpendicular to the surface. And number four is that charges accumulate at points. So what would one of those look like? Let's say we got like a potato looking thing over here. First thing is that the electric field is zero inside of there, that the electric field at every single point is pointing directly away from the surface. Let's say this guy right here is a positively charged thing. So we have excess protons compared to our electrons. That's what the electric field would look like. The positives would all be near the surface. So all of the neutral stuff would be near the center, meaning the place where all the electrons were removed from was the outside. And you notice if the center of mass and center of charge is right here, then that means the furthest away point from them is going to be these edges, and that's why the charges are going to want to move as far away from the center of charge as they can. So let's say we've got a neutral hollow conductive sphere. And I'm going to place a positive charge at the center. So inside of the hollow sphere, I place a positive charge at the center. What I want you guys to do is to draw the electric field lines for this. So let's say here's my sphere. It's not infinitely thin, so it has some amount of surface. And at the center, I'm going to put a positive there. What I want you guys to do is draw the electric field lines for this. So take a second, pause the video, we'll come back and go over it. All right, so looking real quick, what's going to happen is all the electrons are going to pile up near the inside because they're going to want to get close to that positive. That means on the outside, we're left with a bunch of positive charge, which means to the outside surface of this, it basically just looks like a metal sphere with a positive charge. All of my electric field lines are going to be coming straight off of the sphere. And remember, on the inside, there should be none because it's in electrostatic equilibrium. Once all of these charges have gone into place, there's no longer any electric field lines inside of there, because if there were, then charges would still be moving around. So inside the sphere, no electric field. Outside the sphere, this acts like a point charge, just missing an electric field right in the middle. Now we're going to go into doing a little bit of math using our electric field lines. All right, in this first one, I'm going to work through it with you since it's our first time doing anything with electric field. It's very similar to electric force. It's just -1 Q charge. So on this first one, I want to find the electric field at point A. I've got a charge Q1 over here, Q2 over there. Both of them are negative charges. This one has double the value. So let's go ahead and solve for it. Electric field this is my electric field caused by Q1. And remember, electric field is a vector, so the direction does matter. K, Q1 over R squared. And then down here, we've got our electric field Q2, which is equal to K, Q2 over R squared. When I plug in these values, 9 times 10 to the 9 Newton meters squared per Coulomb squared, times our charge, which is going to be negative 8 times 10 to the -6 coulombs, divided by 0.30 meters. We'll square that. Same thing down here, except now we just change our distances. Times -4 times 10 to the -6 coulombs, divided by 0.20 meters squared. When I plug those values in, I get 8 times 10 to the 5th newtons per coulomb. That's our unit for electric field. It makes sense because it's saying how much force do you get for a given charge at that point. And then down here, I get 9 times 10 to the 5th newtons per coulomb. These both should be negative, but I didn't worry about the sign because I just want to think about it physically. Electric field points the direction a positive charge would go. If I've got a negative charge over here, a positive charge would want to go that way. So we should have this one to the left, negative charge, so it's going to want to go that way. And again, stronger charge doesn't necessarily mean stronger electric field. Like we see in this case, we end up with more electric field to the right. So our total electric field, our E tot or our E net, is going to be 1 times 10 to the 5th newtons per coulomb, and it's going to be rightward. Now we're going to have you guys work on a problem. So for this last problem, we've got a point A that I want you to find the electric field at. Down directly below it, we have a charge Q1 that has a charge of 50 microcoulombs. And then over here at half a meter to the right, we have a charge Q2 with -60 microcoulombs. So your job's going to be to figure out what it is. I'll remind you that, or give you the hint that it'll be very similar to the way we solved for electric force. It's just going to be different by a factor of that charge being at A. This is just a point. Before we were looking at what force something would feel with a charge. So go ahead and try this out. I'm going to pause the video, and when we come back, we'll go over it. All right, you see a big wall of text? Don't worry, we're going to break it down. So first thing we want to do is we want to solve for our electric force, our electric field caused by charge Q1. KQ over R squared, just normal. And then because it's a positive charge, remember electric field shows the direction a positive charge would go. If I put a positive charge right here, it wants to go up and away. So we should have it pointing up. Then we've got this dotted line here, R2. This is the line between A and Q2. Q2 is negative, so it should be pointing down towards Q2. I can just plug my numbers in. First thing I got to do is solve for what R2's value is. So I just come over here, Pythagorean theorem, square it, take the square root of the sum, get 0.58 meters. Put that down here, and what I get is 1.6 times 10 to the 6 newtons per coulomb. Now, with that, I need to break things up into an x and y component. That way I can figure out where the resultant vector is for E1 and E2 combined. So we know E1 is just straight up, so that's a positive y value, so that's 5 times 10 to the 6 positive because it's straight up and it's not moving in the x direction at all. We need to know the angle of R2, so that way the angle above horizontal, so that we can solve for it. So we can solve for the components of R2. When I do that, 31 right there, break down my triangle here, use sine and cosine to figure out what my values of the x and y components of E2 are. Plug them in here. Since it's moving to the right, right is positive x, so we end up with a positive value. It's pointing down at it. It follows along this line, so we should get a negative value for y, and that's what I see here. Next thing, I'll just add them up so that I can find out my components of E2, and then I'm just going to turn it back into a triangle. Here are my x and y components. There's E tote. I got to figure out my angle. Once I do that, just take the inverse tangent, opposite over adjacent. I get 71.6 degrees, so that's north of east. And then the value for my E tote is just the Pythagorean theorem for that triangle. And I get 4.4 times 10 to the 6th. And that is it for electric fields.